Hi, Kerry. Thanks for taking the time to view the presentation. Before we get into the methods and results, I'd like to take a moment to just sort of give you an idea of how the presentation's laid out. It's going to be about 15 minutes, as we talked about, and the first thing I want to do is sort of give you an overview of the project so we reorient ourselves to where we are. After that, I'm going to get into the methods very briefly, but I hope that you can take some time to review the details if you want to get into the details. They will be in the PDF packet that I sent you along with this link. After the methods, I'm going to spend most of the time talking about the results and the implications of those results. And finally, we'll sort of summarize everything into a neat package. But once again, I hope you can take some time to review the PDF packet that I sent you. It has much more detail than on how we derived all of these measures, much more detail than what I'm going to get into here. So really quickly, an overview of the project. On the left, we see sort of the current model of how teams understand the interface between the driver and the vehicle. As we know, a lot of data is recorded from the vehicle itself, but the teams don't really record physiological data from the drivers. Instead, the engineers and the mechanics rely on oral communication from the drivers to describe his impression and performance of the car. Well, our idea is, since you're recording such a rich data set from the vehicle, why not also record neurophysiological data that you can use in an integrated analysis to come up with a much more informed and holistic decision, not only on how to proceed with setup issues, but also to provide training and feedback to the driver so that he can learn to sort of maintain these higher performance states. So to prove this concept, we used a common industry standard racing simulator called R-Factor. It's modified to emulate the characteristics of a 2012 spec F1 car, both in terms of force feedback on the wheel, as well as the physics engine that governs the way that the vehicle interacts with its environment. The software is also modified to allow us to import telemetry data from the simulator into Motec Pro, a software that's similar to McLaren Electronic Systems Atlas. The driver's EEG and the vehicle data are aligned and analyzed for correlations with various measures of performance and vehicle control. The raw data is also collected, logged, and stored for future use, for example, in case of a safety investigation. But this presentation is going to focus on the top part here, the driver neurofeedback training. The other sections are sort of other interests that we have, but for the purpose of this presentation and proof of concept, I want to focus on the main part, which is the correlations between driver brain state and performance on the track, as well as measures of vehicle control. I'm going to discuss these results and their implications on how we evaluate this project. So here's a breakdown of all the different measures that we obtained in our analyses. Each one of these modules is one of the parameters that we analyzed. I'm not going to get into this in detail right now, but if you like, you can take a look at the appendix in the PDF packet I sent, and that explains how each of these is derived in more detail. So basically we have three areas of interest. Number one on the left here, under neural efficiency. Can we measure neural efficiency and peak performance? And is this trainable via neurofeedback? Number two in the middle here is, can we measure the cognitive load of a driver under different vehicle setups and different environmental conditions? And number three on the right here is, can we gain insight on how consistent a driver is by measuring how well he varies his input under different conditions to extract more performance from the car? So before we get into anything, let's get an idea of the general data set that we're talking about. So we gathered data from an experienced driver completing 105 laps in the simulator on one track. This was the Shanghai Grand Prix track. And we chose this track for its demand for a very balanced setup and continuous driver management of the understeer and snap oversteer handling problems. So this is a frequency distribution of the lap times across our data set. Here's a frequency distribution of the sector 1 times. And here's a frequency distribution for sector 2, sector 3, and finally here's a frequency distribution showing the apex speed in turn 16. This is a very demanding mid-speed corner in this track, and we'll talk about this a lot more when we get to the discussion of adaptive variability. So, drivers talk about being in the zone, being switched on, or being on form, and I'm sure you've heard this a lot from your athletes too. So basically, can we quantify this state of peak performance and then use neurofeedback to help drivers learn to achieve it and maintain it longer without sort of interrupting it with their thoughts? So, as you may know, alpha band power is an indication sort of being in this zone. We know from a lot of literature on meditation, on states of flow, on peak performance, that higher alpha band power is usually indicative of sort of the higher cortex disengaging itself and letting the lower areas that have been hardwired with training take over. So here we see that higher alpha band power is actually related to faster lap times in our 105 lap data set. And this is measured in temporal, parietal, and occipital recording sites. So you can imagine a lot of sensory motor integration happening without much interference from the executive system. We see that alpha band power is also related to faster time in sector 1. And again, in the parietal recording site, we see that for sector 2, alpha band power is also related, although we see it more in a frontal site for sector 2, possibly because it's a much more technical circuit, technical sector, as opposed to sector 1, which is a lot more sort of flowing with longer corners. So what happens if we take one of these dots, let's say we take the fastest lap time, and we take an average lap time, and then we take the slowest lap time, and we compare actually the time course of the alpha band. Be interesting to look at that. So what we've done is actually split the EEG signal with an FFT into beta and alpha, and actually graphed the time course throughout the whole lap. So what we're looking at here is the slowest lap. As you can see, we have some alpha band bursts. We also see that the alpha band is much higher amplitude than the beta band as usual. But if we compare this to the sort of average lap time, we see that we have considerably more alpha band bursts. And then if we compare this to the fastest lap, we actually see a big difference between the slowest lap, average lap, and fastest lap. So the way that I would interpret this is that this state of peak performance that athletes refer to as being in the zone is actually predicted by higher mean alpha band power, and drivers will benefit from having feedback about this state using neurofeedback to implicitly learn how to achieve and maintain this state of peak performance. So for example, I'm sure you know experimental setups where you can hook somebody up to an EEG and then give them feedback about a certain brain state, and then eventually they learn how to maintain it implicitly. Basically, this is what we would want to give feedback to the drivers about, so that they can learn how to maintain that state of peak performance without bringing the higher cognitive areas to interrupt it. So let's talk a little bit about cognitive load. We know that teams rely on oral feedback from the driver to inform decisions about grip levels and car setup. Can we actually provide an objective measure of cognitive load that's related to grip level and car behavior? So these three heat maps represent the loci of alpha band activity in three different conditions. On the left is a condition of poor car setup, So I deliberately set up the car to be heavily understeer prone. The middle map is a condition of moderate car setup, so this is more manageable compared to the left map. And finally, the map on the right is the power location during the fastest lap. So as we can see, higher cognitive load is related to a more frontal loaded EEG power, whereas a low cognitive load, high neural efficiency, is related to a more sort of temporal, parietal, and occipital loaded alpha band power. So what this suggests to me is that when you're doing your best performance, you're actually letting the more hardwired sensory motor interactions dictate the performance rather than interfering with the executive system. And this is basically this makes it a strong measure of cognitive load. Now we can not only see this spatially, but if we actually graph the mean beta band power against grip level here is a measure derived from tire rotation ratios, among other things. So we actually see that higher beta band power is related to less grip. So basically, the less grip you have, the more frontal beta band power you're outputting, basically the more cognitive load you have. And so this makes the beta band power at frontal recording sites a high indicator of cognitive load that can be used to provide feedback to the teams. So let's talk about adaptive variability. We know that some drivers, let's say Kimi Raikkonen, Fernando Alonso, these drivers are known for being quote unquote consistent. But we actually think that this outer consistency is actually the result of inner variability in behavior. So they're adjusting and responding with very fine variations to respond to small car behavior changes and environmental conditions that others may not be picking up. So can we actually provide an objective measure to measure this adaptive variability that can be maybe used in driver evaluation programs? So here's an analysis of several car behaviors and driver inputs through turn 16 of the Shanghai Grand Prix track. The purple trace describes the behaviors during the fastest lap of the dataset, and the cyan trace is the slowest lap in our dataset. So we see here from the first plot from the top that maintaining higher speed through the trace depends on minimizing oversteer, and this oversteer is on the second figure. We can see it on the second plot from the top. So you can also maintain the higher speed by using smoother steering input and punctuate the steering input with small and fast micro corrections, and that's on the third plot from the top is the steering input. And then finally, having a smoother, adaptive, and oscillating throttle input. So you can see that on the fourth plot from the top, the driver is actually feathering the throttle to respond to small changes that he's picking up about wheel spin and loss of grip at the rear. This is another marker that we can use for adaptive variability. And finally, on the bottom there, later braking but smoother braking is also adaptive for maintaining a higher speed through. So the question is this adaptive variability behavior related to some neurophysiological measures? So we actually see that the higher apex speed values are correlated positively with alpha band power at the temporal recording sites. So this is very interesting because this means that alpha band power is related to adaptive variability, and not only can you spot this sort of micro correction behavior from looking at the data from the car, but you can also actually have a neurophysiological marker of that special consistent adaptive behavior from very special drivers. And we think that driver evaluation programs will benefit from having a tool that actually quantifies this. So finally, the last thing I want to talk about is connectivity. We're still actually not so sure how to interpret this, but I hope that you'll take 30 seconds or so to review this with us. It is kind of interesting, and this is kind of a supplementary analysis that we ended up doing. So here we're actually looking at the node centrality of P8, so the parietal recording side. Node centrality simply means, on average, how synchronized are other nodes to this node. So this is sort of like measuring how much of a hub this node is. And we actually see that the centrality measure correlates nicely with how fast the sector time is for sector 1. And this is pretty interesting. If we take one of the fastest laps and then look at the connectivity for that and compare it to an average lap and a slower lap, this is what we get. So as you can see, the connectivity in the slower laps is much lower. Connectivity in the faster laps is much higher. And this is kind of interesting because this means that there's a lot more integration happening in the motor cortex, and there's a lot more just sort of synchronization across different brain regions. So this may be a different supplemental measure of neural efficiency that I thought I would share. So finally, just to summarize everything, mean alpha band power at left frontal, right temporal, parietal, and occipital sites is higher during faster laps and sectors. Low grip conditions correlate with higher frontal band power, and adaptive variability is correlated with higher alpha band power for sectors with higher apex speed maintained through the corner. So with that, I'll basically leave you to evaluate the opportunity. I hope that you'll take the time to review the supplemental slides that I gave you as well to get an idea of how these measures were derived. And I look forward to having a nice discussion with you soon. Thanks again for listening. Have a great day.